So this is Calculus Lecture 6, and again, I started by saying CUNY is closed on Monday for Washington's birthday, but we have class on Tuesday because CUNY follows a Monday schedule next Tuesday, and then we're back to regular class schedule. So next week we meet Tuesday and, of course, Wednesday. And I reviewed some differentiation rules. Derivative of a constant is 0. Derivative of x to the power n is nx to the n minus 1. Derivative of a constant times a function is a constant times the derivative. The derivative of the sum or difference of two functions is the sum or difference of the derivatives. And then if you put that together, you can then differentiate any polynomial term by term in a very simple way. And in mathematics, we have important numbers 0, 1, pi, and e, which is a 2.718 something. And e has this property that the limit of e to the h minus 1 over h, as h goes to 0, is 1. So this is really a theorem in more advanced calculus, but that's a property of the number e. And using that property, we can compute the derivative of the exponential function e to the x, right? That function looks like that. E to the 0 is 1, but graph of y equals e to the x goes like that. It's always positive. It approaches 0 as you go to minus infinity, and it approaches plus infinity as you go to plus infinity. So what is the derivative of e to the x? This will be the limit as h goes to 0 of e to the x plus h minus e to the x over h. That's the definition of the derivative. But the exponential function has the property that e to the x plus h is e to the x, e to the h. Every exponential has this property. So this is the limit as h goes to 0 of e to the x, e to the h minus e to the x over h. And I can factor e to the x from this. Is e to the h minus 1 over h. And with respect to h, e to the x is fixed, it's constant. So this is e to the x times the limit of e to the h minus 1 over h as h goes to 0, and that limit is 1. So we have the following miraculous property that for the exponential function, the derivative of e to the x is e to the x. This is actually one of the most important facts in calculus, that the rate of change of the exponential function is equal to itself. So now we can solve some geometrical problems on curves, finding tangent lines, using our derivative rules. Suppose we have the curve f of x equals 2x minus e to the x over 2. And we want to find the tangent line at the point when x is equal to 0. And when x is equal to 0, f of x is 2 times 0, which is 0, minus e to the 0, which is 1 over 2, minus a half. So to find the tangent line, remember the tangent line to y equals f of x at the point x equal a is what? It's the line through the point a comma f of a on the curve with slope f prime of a. So we use the point slope formula for a line, we get y is equal to the slope f prime of a times x minus a plus f of a, right? This is a formula you have to know by heart. When we take the midterm in a few weeks, a month, you're not going to have a cheat sheet with you or a list of formulas. This is something you have to know. This is a basic piece of what really is pre-calculus or high school algebra. You have to know it. So here's our function, f of x. So f of 0, we already calculated, 2 times 0 minus e to the 0 over 2, which is minus a half. But we need the derivative. So the derivative with respect to x of 2x minus e to the x over 2. That's the 2 times the derivative with respect to x of x minus a half the derivative with respect to x of e to the x. That's just using our basic differentiation rules. The derivative of x is 1. 2 times 1 is 2. The derivative of e to the x is e to the x, so minus a half e to the x. That's the derivative. That's f prime of x. So f prime of 0 is 2 minus e to the 0 over 2. Anything raised to the 0th power is 1, and 2 minus a half is 3 halves. So what is the tangent line? It's y equals the derivative 3 halves x minus 0 plus f of 0, which is minus a half. So y is 3 halves x minus a half. That's the tangent line. Right? A question about that? Let's see. I'm trying to open a Maple window so I can. But my computer seems to be misbehaving. I'll open an old version of Maple, see if that works. Okay, let's see if I can do this in Maple now. Let me try to share the screen. Okay, so you should see a Maple window. And we were looking at the function 2x minus e to the x over 2. So x goes to 2 times x minus exp of x, that's e to the x, over 2. And if I want to plot f of x, that's what the function looks like. Let me just plot it maybe from -5 to 5. That's a little better. And maybe just -5 to 4. Yeah, okay. So that's the graph of the function, but I want the tangent line. So I'll just call tangent line, I'll just call it TL for tangent line. And what is the tangent line? Let's use the formula. It's the derivative of f at 0 times x minus 0 plus f evaluated at 0. That's the tangent line. So now if I want to go back and plot the two of them together, so the way you plot two functions together is put them in curly brackets. So curly bracket f, comma, TL was the name I just gave to tangent line. There it is. There you can see the red is the function, the green is the tangent line. There's a better picture. Yeah, pretty nice actually. What you can do with Maple. Okay. Any questions about this so far? All right, now I should make one other remark. Differentiating functions, of course, is fun. So if you want to increase the fun, you can differentiate over and over again. So suppose I have a function like f of x equal to, I don't know, x cubed. Then you differentiate it once, you get 3x squared. That's the first derivative. But I could differentiate the derivative. That's the second derivative. I'll put f double prime of x. When you differentiate this, you get 6x. I could differentiate it again, the third derivative. Derivative of 6x is 6. I can differentiate it again. The fourth derivative is the derivative of the third derivative. That's the derivative of the constant function 6. Derivative of a constant is 0. And in fact, if we keep on differentiating, it's always 0. Fifth derivative and so forth, because once it's 0, it's 0. So in general, we can define the nth derivative of a function I can write this fn like this. This means nth derivative. The way you get the nth derivative is to calculate the n minus first derivative and then differentiate that. Okay. So if you take f of x equal to e to the x, first derivative is e to the x. Derivative of e to the x is e to the x. If I take the second derivative, I'm just differentiating e to the x, it's e to the x. And the third derivative is e to the x. And in fact, for the exponential function, since every time you differentiate e to the x, you get e to the x, if you just repeat this n times, it's always e to the x. This is true for all n. Very important property of the exponential function. Okay. Now, we talked about the derivative of the sum and difference of two functions, but there are other arithmetical operations you can do on functions. You can multiply them and you can divide them. So for multiplication, we have the product rule. If we take functions f of x and g of x and we multiply them, and then we differentiate the product, this is the derivative of the first factor, f prime of x, times the second, plus the first factor times the derivative of the second. So for example, if you have x cubed e to the x, and you want to differentiate that, that's the derivative of the first factor times the second, plus the first factor times the derivative of the second. Derivative of x cubed is 3x squared times e to the x, plus x cubed, and the derivative of e to the x is just e to the x. So if I can factor out e to the x, I get 3x squared plus x cubed e to the x. Or if I want, I could write this as 3 plus x times x squared, because I can factor that times e to the x. Okay. How do we prove the product rule? Right? These things aren't made up. They somehow come out naturally from the definition. So the derivative with respect to x of f of x, g of x, this is by definition the limit as h goes to 0 of f of x plus h, g of x plus h, minus f of x, g of x over h. That's the definition of the derivative. And I can compute this by being a little bit clever. This is the limit as h goes to 0, something over h. So I have f of x plus h, g of x plus h, and I have a minus f of x, g of x. I'm going to add and subtract the same thing just to give me something I can calculate. I'm going to subtract minus f of x, g of x plus h, and I'm going to add f of x, g of x plus h. So these two cancel, so I've just added 0 in a clever way. What is this? This is the limit as h goes to 0. I have these two factors. I have these two, and this. From this, I can factor out g of x plus h. This is f of x plus h minus f of x times g of x plus h over h. And from this, I can factor out f of x. I have g of x plus h minus g of x over h. So when I add and subtract this, I can rewrite this in this form. Now, what happens as h goes to 0? This is exactly the difference quotient that defines the derivative. This is f prime of x. And as h goes to 0, g of x plus h goes to g of x. And here I have f of x, which doesn't depend on h. And as h goes to 0, this goes to g prime of x. And that's the proof. So that really is a rigorous proof of the product rule. And we also have a quotient rule. So this is the product rule. The quotient rule looks similar, but you have to be a little bit careful about one point. So this is the quotient rule for derivatives, if I take f of x divided by g of x, and this is only where g of x is not 0, otherwise you couldn't divide. So I take this quotient and I want to find the derivative. And the rule is this is also going to be a quotient. It's going to be the derivative of the numerator times the denominator. And we also have a term which is the numerator times the derivative of the denominator. In the product rule, we add them, but in the quotient rule, we subtract. And this is also a quotient where the denominator is the old denominator squared. So there's no derivative in the denominator, but it's f prime g minus fg prime over g squared. And again, using the definition of the derivative, one can prove this from scratch, but I'm not going to do that now. Let's just look at some examples. Suppose I take the rational function x squared plus 3x plus 4 over x squared minus 1, and I want to differentiate that. So this is going to be a quotient. The denominator of the derivative is the square of the denominator. So x squared minus 1 is the denominator, and we square that. And the numerator of the derivative, you take the derivative of the numerator. What's the derivative of x squared plus 3x plus 4? If you differentiate term by term, you get 2x plus 3 times the denominator. And then minus the numerator times the derivative of the denominator. The derivative of x squared minus 1 is 2x. So this is over x squared minus 1 squared. You see, that's actually calculated. If I multiply this out, I get 2x cubed plus 3x squared minus 2x minus 3. And if I multiply this out, I get 2x cubed plus 6x squared plus 8x. So it looks like the 2x cubes cancel. 3x squared minus 6x squared is minus 3x squared. Minus 2x minus 8x is minus 10x minus 3. Or if you like, let's take out the minus sign. This is minus x squared minus 1 squared, 3x squared plus 10x plus 3. That's the answer. Suppose we wanted the derivative of e to the minus x. You know the derivative of e to the x is e to the x, but what is e to the minus x? Well, we can use the quotient rule because e to the minus x is the same as 1 over e to the x. So this is now a quotient. So when you differentiate this, you get the denominator squared in the bottom. In the numerator, you get the derivative of 1 times e to the x minus 1 times the derivative of e to the x. The derivative of the constant 1 is 0, so this term is 0. Derivative of e to the x is e to the x, so this is minus e to the x. E to the x squared is e to the 2x, so this is minus 1 over e to the x, or minus e to the minus x. Okay. Any questions about this? Okay. So we know how to differentiate powers of x, which means we know how to differentiate polynomials, and we know how to differentiate rational functions, which are quotients of polynomials, all using the derivative rules. And we know how to differentiate e to the x, but there's some other basic functions in mathematics, like the trig functions. Sine and cosine are the most important. So we would like to find out what is the derivative of the sine of x and what is the derivative of the cosine of x. And we'll prove right now that the derivative of the sine is the cosine. And the derivative of the cosine is not the sine, it's minus the sine. So these are fundamental rules that we like to prove. And the proof depends on some geometrical facts. One is that, so this is a theorem already in the book, that the limit of sine x over x. So, you know, what does the sine function look like? Sine function looks like that. At x equals, so this is y equals sine x. At x equals 0, it's 0. So as x goes to 0, sine x goes to 0 and x goes to 0. This limit may or may not exist. In fact, it does exist, and the theorem says that this limit is equal to 1. And it's based on just some simple geometrical properties of the circle. So suppose this is the upper half of the unit circle. So this is a circle, what's called the unit circle. That means the radius of the circle is 1. So this would be the point 1, 0, 0, 1, minus 1, 0. So let's say we take an angle x measured in radians. So x means the length of this arc. Let's draw these two perpendicular lines. So let's see where this, you take the angle x, where one leg is the positive x-axis, and this point where it hits the circle, we'll call A. And if you drop the perpendicular, this is D. This point C is where the circle hits the x-axis. You draw this perpendicular, and we'll call this point B. So here I'm taking an angle x in the first quadrant. So we have an angle x between 0 and pi over 2. And again, in calculus, we only measure angles in radians, right? So the length, the size of the angle x is exactly, the radian measure is the length of the arc of the unit circle that the angle x cuts out. Now, if I look at this picture here, this is the triangle OAD. So I have the area of triangle OAD. That's this. And I have the sector OAC. And I also have, so that has a certain area. And then I also have the area of the triangle OBC. And you can see this triangle is included in the sector, so this is less than this. And the sector is included in the bigger triangle, so the area of the sector is less than the area of the big triangle. What are these areas? Area of a triangle is half the base times the height. This is the base. This is the height. So this is 1/2 the base OD times the height OA. Now, let me just remind you, if you have an angle X, and you have this right triangle where this hypotenuse is length 1, the coordinates of this point are cosine X, sine X. That means this distance is cosine X, and this distance is sine X. So OD is the cosine, this would be AD. AD is the sine. This is 1/2 cosine X, sine X. The area of triangle OBC is 1/2 the base times the height. This base is 1. And the height, this over this, that's the tangent. Right? BC over OC is the tangent of X, which is sine X over cosine X. And the area of the sector, well, the area of a circle of radius 1 is pi. If you take a fraction of the circle, x radians, what fraction of that? That's x over 2 pi. So x over 2 pi of pi is x over 2. The sector has area x over 2. So I get an inequality which says, I multiply through by 2, cosine x sine x is less than x is less than sine x over cosine x. If I rewrite that, that says cosine x is less than sine x over x is less than 1 over cosine x. As x goes to 0, the cosine goes to 1. So this is going to 1, this is going to 1, this is squeezed in between. So this also goes to 1. So that's the proof. That's a proof of this identity. In 100-level classes, it's not the proofs you have to know, it's the results, but it's important to know these things have proofs that are often very lovely. This is an example of such a proof. So now let's compute the derivative of the sine and then the derivative of the cosine. Let's see. So you have to know the addition formulas. You have to know that sine of x plus h is sine x cosine h plus cosine x sine h. And the cosine of x plus h is cosine x cosine h minus sine x sine h. So this is something, this is a bit of pre-calculus, trigonometry, that you're supposed to know. And we just proved that the limit of sine x over cosine x is 1. So the limit of sine x over x is 1. So we know the limit sine x over x, as x goes to 0, is 1. We also like to know cosine x minus 1 over x. As x goes to 0, cosine goes to 1, so the numerator goes to 0, and the denominator goes to 0. But I can use some trig identities as follows. Cosine x minus 1 is equal to cosine x minus 1, cosine x plus 1. I can multiply by cosine x in the numerator if I also put the same thing in the denominator times x. I just multiplied by 1. But now what I have in the numerator is cosine squared x minus 1 over x times cosine x plus 1. What's cosine squared minus 1? Well, the most important trig identity is that cosine squared x plus sine squared x equals 1 for every angle x. So cosine squared x minus 1 is minus sine squared x over x times cosine x plus h, which I can write as minus sine squared x is sine x times sine x. So this is sine x over x, sine x over cosine x plus 1. So this is just a way to rewrite this thing. And so what is the limit as x goes to 0, cosine x minus 1 over x? As x goes to 0, sine x over x goes to 1, sine x goes to 0, and cosine x plus 1 goes to 2. And 0 over 2 is 0. So we get this is equal to 0. So in order to calculate the derivatives of the sine and the cosine, I need these two formulas. So let's use those formulas right now. So the derivative with respect to x of the sine of x is the limit as h goes to 0 of sine of x plus h minus sine x over h. Let's examine this. Sine of x plus h minus sine x. Well, sine of x plus h is sine x cosine h plus cosine x sine h minus sine x. And here I have a sine x, and here I have a sine x. So I can subtract. This is sine x cosine h minus 1 plus cosine x sine h. And now I'm going to take this expression and divide by h. I get sine x times cosine h minus 1 over h plus cosine x sine h over h. Now, as h goes to 0, so what happens as h goes to 0? Cosine h minus 1 over h goes to 0. Cosine x goes to 1, and sine h over h, as h goes to 0, is 1. And 0 plus 1 is 1. Sorry, as h goes, this doesn't depend on h. This is cosine x times 1, so this is cosine x. As h goes to 0, I'm looking at this difference quotient. The limit as h goes to 0 of sine of x plus h minus sine x over h. Using my trig identities, I can rewrite this expression like this. And as h goes to 0, this goes to 0, so this term disappears. This is cosine x, that doesn't change with x, but this goes to 1. So my limit is just cosine x. So that's the proof that the derivative of the sine is the cosine. And I can get the derivative of the cosine in a completely similar way using my trig identities. So I have the cosine of x plus h is cosine x cosine h minus sine x sine h. And from this I subtract cosine x. So from here and here, I can factor out cosine x. And I have cosine h minus 1 minus sine x sine h. So that's the cosine of x plus h minus the cosine of h, cosine of x. If I divide by h, I get this quotient. What is the limit as h goes to 0? Cosine x doesn't change. This is cosine x, but this goes to 0. Minus sine of x, and as h goes to 0, sine h over h goes to 1. So this disappears, and I get minus sine x. So that's the proof of my two trig differentiation formulas. And from them, I can figure out the derivatives of all the other trig functions. For example, the tangent. Suppose I want to know the derivative with respect to x of the tangent of x. Well, every trig function can be written in terms of the sine and the cosine. This is the derivative of sine x over cosine x. That's the definition of the derivative. I use the quotient rule. I get something with cosine squared x in the denominator. Here I have the derivative of the sine times the cosine minus the sine times the derivative of the cosine. The derivative of the sine is the cosine. So I get cosine x times cosine x. This is all over cosine squared x. Minus sine x times the derivative of the cosine, which is minus the sine. So I have cosine squared x. Cosine times cosine is cosine squared. Minus times minus is plus. Sine times sine is sine squared. And cosine squared plus sine squared is 1. So I get 1 over cosine squared x, which is the same as 1 over cosine x squared. And you need to remember that 1 over the cosine is the secant. So this is the secant of x squared. So this is a proof that the derivative of the tangent is secant squared. Let's compute the derivative of the secant. That's kind of fun. Remember, secant x, the definition of the secant is 1 over the cosine. So the derivative of the secant is the derivative of 1 over the cosine. By the quotient rule, I have cosine squared x. I have the derivative of 1 times the cosine minus 1 times the derivative of the cosine. Cosine squared x is still in the denominator. Derivative of 1 is 0, so this term disappears. And minus the derivative of the cosine is minus the sine. So minus the sine is plus the sine. So it's sine x over cosine squared x. Or if I like, I can write that as sine x over cosine x times 1 over cosine x which is tangent x times secant x. So the derivative of the secant is tangent times secant. All right, well, we're now able to differentiate many functions, and let's do some practice problems. Let me just look at problems at the end of this very nice section. There are also some limits that we can do that are useful. So these are the exercises at the end of section 3.5. So this is section 3.5 in the text. Let's look at number 11. What is the limit as x goes to 0 of sine 3x over x? Well, we know the limit as x goes to 0 of sine x over x, but this is different. But I can write this like this. This is the limit as x goes to 0 of sine 3x. If I have a 3x in the denominator, I'm multiplying the denominator by 3. I'm multiplying the numerator by 3. So I can write this as 3 times sine 3x over 3x. And the 3 I can take outside the limit. So this is 3 times the limit as x goes to 0 of sine 3x over 3x. So now I have the same quantity here and here. If I were to let, for example, 3x equal t, this is exactly the same as 3 times the limit of sine t over t as t goes to 0. Because as x goes to 0, 3x goes to 0. This limit is 1, so I get 3 times 1. So this limit is 3. It's not 1, it's 3. This is a very, very useful trick in calculus. Let's look at number 13. The limit as x goes to 0 of sine of 7x over sine of 3x. Now I know what the limit of sine x over x is, so let me write this like this. This is the limit as x goes to 0 of sine of 7x over sine of 3x. If I multiply numerator and denominator by 1 over x, I can write it like this. And I can write this as the quotient of these two limits. Limit as x goes to 0, sine 7x over x over the limit as x goes to 0, sine 3x over x. If I make this a 7 and multiply by 7, and if I multiply top and bottom here by 3, this is, the numerator is 7 times this limit. That limit is 1. Here, this is 3 times this limit is 3. So this limit, if I do this technical change, I can see the limit is 7/3. Okay. Really, you should look over the problems on page 176, 177. If you see any that you'd like me to do right now, just ask me to do them. I'm just going to pick some that are interesting. So this is number 23. Suppose y sine x plus cosine x. Then dy dx is the derivative of the sine, which is the cosine, plus the derivative of the cosine, which is minus the sine. So If y is sine x plus cosine x, the derivative is cosine x minus sine x. Suppose I had the product sine x times cosine x. Then by the product rule, the derivative will be the derivative of the first. That's the derivative of the sine is the cosine times the cosine plus the derivative plus the sine times the derivative of the cosine, which is minus the sine. So I get cosine squared x minus sine squared x, which you should recognize is the same as the cosine of 2x. This is the addition formula for the cosine. Let's look at number 57. Suppose I have y equal x sine x, and I want to find the second derivative. So by the product rule, the first derivative is the derivative of x times sine x plus x times the derivative of sine x, which is cosine x. So y prime is sine x plus x cosine x. If I differentiate again, the derivative of the sine is cosine x plus, what's the derivative of x cosine x? The derivative of x, which is 1 times cosine x plus x times the derivative of the cosine, which is minus sine x. So it looks like I get 2 cosine x minus x sine x. Cosine x plus cosine x is 2 cosine x. Let's look at number 72. We have the function y equals 4 sine x cosine x. At the point x equal pi over 3 radians, we want to find the equation of the tangent line. And then it says use a graphing utility to plot the curve in the tangent line. Okay, well, let's see. So this is my function. What is dy dx? Dy dx by the product rule, it's 4. Derivative of the sine is the cosine times the cosine, cosine squared, plus sine times the derivative of the cosine, which is minus the sine. So I get minus sine squared x. Or I can write this as 4 times cosine 2x. So what is the tangent line at the point pi over 3? Let me just call this function f of x. So f at pi over 3 is equal to 4 times the sine of pi over 3 cosine of pi over 3. you have to know what these angles are and what their cosines are. Pi over 3, this point is a half root 3 over 2. The sine is root 3 over 2, and the cosine is a half. So this is 4 times root 3 over 2 times a half. 2 times 2 is 4, cancels this 4. This is root 3. So f at pi over 3 is root 3. So f of pi over 3 is the square root of 3. What's f prime of pi over 3? This is pi over 3. This is f prime. It's 4 times the cosine of 2 times pi over 3. That's 4 times the cosine of 4 pi over 3. This is 4 pi over 3. The cosine is minus a half. Yeah, minus 2. So the tangent line will have the equation y equals the derivative minus 2 times x minus pi over 3 plus the value of the function at pi over 3, which is root 3. So if this is correct, this is minus 2x plus 2 pi over 3 plus root 3. Let's see what this looks like. Normally I would check this by hand, but since I have Maple here, let me share the screen with Maple again. So here I have a new function. Maybe I'll call it g. So this is the function 4 times sine of x times cosine of x. So if I plot, oops, let me spell plot correctly. Plot g of x with respect to x. For a trig function, Maple likes to plot from minus 2 pi to pi. That's what it looks like. And my tangent line, let me call it tangent this time. I'll call it tangent line. My tangent line is the derivative of g at the point pi. Pi in Maple is capital P lowercase I, pi over 3. Times x minus pi over 3 plus the value of the function at pi over 3. Looks like just what I got before. Now, if I graph the two together, so inside curly brackets, this time I'm going to write g of x and tangent line. So there's the curve with the tangent line. Let me just blow this up a little bit. Maybe I'll just graph this from minus 3 to 3. There we are. Isn't that a pretty picture? So here's my curve. And here, pi over 3 is a little bit bigger than 1. And there's the tangent line. Looks very good, I must say. If I want this drawn to scale, I right-click and go to Scale and Constrain. And that's really what it looks like. Yeah, there it is. So this is now drawn to scale. And here is this function, and here is the point pi over 3. The green line is the tangent line. That's really pretty nice. Any questions about this? Or about anything that we've been doing so far today? We're covering a decent amount of material, and it's done very well on MindLab. So let me just give as a hint of coming attractions. This is what I'm going to prove next week. You have the notion of composite functions in mathematics, and in particular, right here in calculus. And so you might have some set of numbers, some function g that goes from here to here. And then you have a second function f that goes from here to here. So if you take a point x, this gets sent to the point g of x, and then g of x is sent by f to f of g of x. So this function you get by doing one function followed by the other, we write as f circle g. That means this is composition. That's what this notation means. But so f circle g of x, this means f of g of x. And the chain rule gives a way to differentiate composite functions. It says the derivative with respect to x of f of g of x is equal to the derivative of f evaluated at g of x times g prime of x. So this is a somewhat complicated formula, and it's used all the time. Let me just give an example. Suppose g of x is the function x squared, and f of the function is sine of x. So f of g of x, this means the sine of g of x. And g of x is x squared. This is the sine of x squared. So the derivative with respect to x of the sine of x squared, that's a complicated function. This is the derivative with respect to x of f of g of x. We can look at this as this composite function. So this is f prime evaluated at g of x times g prime of x. Now, if f of x is the sine, f prime of x is the cosine of x. So f prime of g of x, this means the cosine of g of x times g prime of x. If g of x is x squared, g prime of x is 2x by the power rule, times 2x. Let me just write this. This is 2x times the cosine. What is g of x? Of x squared. So the derivative of the sine of x squared, it's not the cosine of x squared, it's 2x times the cosine of x squared. That okay. So we'll talk about that a lot next week. And the chain rule is the rule that we use the most often for derivatives. So again, I would urge you to do as much as you can of the exercises in MyLab and to study the book as much as you can, because this is hardcore calculus. This is the kind of thing which you absolutely, positively must know thoroughly in order to do well in the course. Right. Again, let me remind you, I have a problem session at 1 o'clock today. I have another problem session Friday morning at 11, and other times I can be available by appointment if you send me an email. Okay. All right, well, we're going to quit at this point, I guess. It's supposed to be 60 degrees outside today, so it's a beautiful day, which I hope everyone gets to enjoy it. And remember, no class on Monday next week, but there is class on Tuesday. So I'll see you then. Any last questions before we log off? Okay. Be well, everyone.